Hello there, and welcome to the Deep Rest Science channel. I'm so glad you found your way here, because tonight we're going to embark on a tranquil journey through the awe-inspiring, mysterious world of black holes. Let this be your moment to slow down and unwind. Wherever you are, let the rush of the day fade, the noise soften, and your thoughts drift gently, like starlight, illuminating the vast expanse of the cosmos. Tonight, we'll venture into the heart of one of the most profound and enigmatic phenomena in the universe, black holes. Though invisible to our eyes, they shape the very fabric of space and time, pulling at the edges of reality with their immense gravity. As we explore calming facts about black holes, their formation, their power, and their place in the universe, you don't need to concentrate or remember anything. Simply listen, breathe, and let the mysteries of the cosmos unfold in your mind as softly and endlessly as the night sky. So settle in, get comfortable, and let the quiet wonder of black holes guide you into a peaceful, restful state. First fact: a black hole is a region of space where the gravitational pull is so strong that nothing, not even light, can escape. A black hole is an extremely dense object in space with a gravitational field so intense that nothing, including light, can escape its pull. This occurs because the black hole's gravity warps the fabric of space-time to an extreme degree. The boundary surrounding a black hole is called the event horizon. Once something crosses the event horizon, it can never escape the black hole's gravitational grip. The concept of a black hole arises from Einstein's theory of general relativity, which predicts that massive objects can cause such curvatures in space-time that they trap everything within them, even light. As light cannot escape, black holes are invisible, making them challenging to observe. However, they can be detected indirectly through their influence on nearby objects, such as the orbit of stars or the emission of radiation from accretion disks. 2. Black holes form from the remnants of massive stars that collapse under their own gravity. Black holes typically form when a massive star exhausts its nuclear fuel and can no longer support itself against its own gravitational collapse. During a star's life cycle, it fuses hydrogen into helium in its core, producing energy that counteracts the force of gravity. However, when the star runs out of fuel, it can no longer sustain this balance. If the star is massive enough, usually more than 20 times the mass of the Sun, it will collapse under its own gravity, causing the core to shrink into an infinitely dense point known as a singularity, surrounded by the event horizon. This process results in the formation of a stellar mass black hole. The outer layers of the star are expelled in a supernovae explosion, while the core remains compacted to form the black hole. 3. The boundary around a black hole is called the event horizon. The event horizon is the boundary around a black hole, beyond which nothing, not even light, can escape. This point of no return marks the limit where the escape velocity exceeds the speed of light. Once an object crosses the event horizon, it is pulled inexorably toward the singularity, the point of infinite density at the center of the black hole. While the event horizon itself does not have physical properties or a solid surface, it marks a region where the gravitational effects become extreme. For an observer outside the black hole, an object falling toward the event horizon appears to slow down and fade as it gets closer, due to the bending of light and the time dilation effects predicted by general relativity. 4. The event horizon marks the point beyond which nothing can return. The event horizon defines the boundary where the gravitational pull of the black hole becomes so powerful that not even light can escape. When any matter, radiation, or information crosses this boundary, it is effectively lost to the black hole, and nothing can escape to be observed again. For an outside observer, it may appear as though time slows down for an object falling into the black hole as it approaches the event horizon. This is a result of gravitational time dilation, a prediction of Einstein's theory of relativity. Once an object crosses the event horizon, it is considered to be beyond rescue, and all physical laws as we understand them break down near the singularity. 5. Black holes come in different sizes: stellar, supermassive, and intermediate. Black holes vary greatly in size, mass, and behavior. Stellar black holes form from the collapse of massive stars, typically having masses between 3 and 10 solar masses. These are the most common type of black hole in the universe and are found in binary star systems or in the remnants of supernovae. Supermassive black holes, with masses ranging from millions to billions of times that of the Sun, reside at the centers of most galaxies, including our own Milky Way. Their origins are still not fully understood, but they play a crucial role in galaxy formation and evolution. Intermediate black holes, with masses between stellar and supermassive black holes, are hypothesized to exist, but they are harder to detect. They may form from the merging of smaller black holes or from the collapse of massive star clusters. 6. A stellar black hole forms when a star collapses after burning out its fuel. A stellar black hole is formed when a massive star reaches the end of its life and collapses under its own gravity. During a star's life, it maintains a delicate balance between the outward pressure from nuclear fusion and the inward pull of gravity. Once the star exhausts its nuclear fuel, it can no longer maintain this balance, leading to a dramatic collapse. If the star is large enough, its core will collapse into a singularity, surrounded by the event horizon. The outer layers of the star are often expelled in a violent supernova explosion. The result is a black hole with a mass typically between 3 and 10 times that of the Sun. These stellar black holes are scattered throughout the universe and are often detected by their effects on nearby stars or by the X-rays emitted from the material being pulled into them. 7. Supermassive black holes are found at the centers of most galaxies, including the Milky Way. Supermassive black holes, SMBHs, are found at the centers of most galaxies, including our own Milky Way. These black holes can have masses ranging from millions to billions of times that of the Sun. The exact process by which supermassive black holes form is not yet fully understood, though it is believed that they may grow through the gradual accretion of gas and dust over billions of years, or through the merging of smaller black holes. The presence of a supermassive black hole in a galaxy plays a central role in the galaxy's evolution. The immense gravitational pull of these black holes influences the motion of stars and the structure of the surrounding galaxy. Observations have shown that galaxies with more massive black holes tend to have higher rates of star formation, suggesting a deep connection between black holes and galaxy formation. 8. The Milky Way's supermassive black hole is called Sagittarius A. The Milky Way's supermassive black hole, named Sagittarius AE, pronounced Sagittarius A star, is located at the center of our galaxy, about 26,000 light-years away from Earth. It has a mass of approximately 4 million times that of the Sun. Sagittarius A4 was first identified through its radio emissions. which were detected in the 1970s. Over the years, astronomers have gathered evidence for its existence by observing the orbits of nearby stars, which move in ways that suggest a supermassive object with strong gravitational influence. In 2019, astronomers captured the first ever image of a black hole, located in the center of a distant galaxy, using the Event Horizon Telescope, which indirectly confirmed the existence of black holes like Sagittarius AR in the centers of galaxies. 9. Black holes do not suck everything around them. They only affect objects that pass too close. A common misconception is that black holes suck everything around them, but this is not the case. Black holes only affect objects that venture too close to them. If an object, such as a star or planet, stays far enough from a black hole, it will orbit it in much the same way that Earth orbits the Sun. It is only when an object passes the event horizon, the critical boundary, that it is trapped and cannot escape. This is because the black hole's gravity becomes so intense near the event horizon that the escape velocity exceeds the speed of light. However, far from the black hole, its gravitational influence is much weaker, and objects can safely orbit without being pulled in. 10. The first direct evidence of a black hole was observed in 2015 via gravitational waves. The first direct detection of a black hole came in 2015 through the observation of gravitational waves. These are ripples in space-time caused by the acceleration of massive objects, such as when black holes merge. The detection was made by the Laser Interferometer Gravitational Wave Observatory, LIGO, which captured waves produced by the collision and merger of two black holes, each about 30 times the mass of the Sun. This groundbreaking discovery provided the first direct evidence of the existence of black holes, confirming many of the predictions made by Einstein's theory of general relativity. Since then, numerous other gravitational wave events have been observed, further enhancing our understanding of black holes and their interactions. Here are the next 10 facts with descriptions. 11. Black holes can be detected by observing the way they affect nearby stars and light. Although black holes are invisible because light cannot escape them, their presence can be inferred by observing their gravitational effects on nearby stars, gas, and light. For instance, when a black hole is in a binary system with a companion star, the gravitational pull of the black hole causes the companion star to orbit in an unusual way. By studying the orbit of the star and applying Kepler's laws of motion, scientists can estimate the mass of the unseen black hole. Additionally, black holes can also affect the light from surrounding material. If a black hole pulls in gas and dust, the material forms an accretion disk, which heats up to extremely high temperatures, emitting X-rays and other forms of radiation. These signals can be detected by space telescopes, allowing astronomers to locate and study black holes indirectly. 12. The concept of a black hole was first proposed by John Michell in 1783. The idea of a black hole was first proposed long before modern science confirmed their existence. In 1783, British scientist John Michell suggested that there could be objects in space with gravity so strong that not even light could escape them. He used Newtonian physics to describe what he called dark stars, which were massive objects with a gravitational pull so intense that light could not escape from them. While Michell's ideas were speculative and based on classical physics, his concept laid the groundwork for the modern understanding of black holes. However, it wasn't until Albert Einstein's theory of general relativity, published in 1915, that the concept of black holes was formally integrated into modern physics. 13. Albert Einstein's theory of general relativity predicted the existence of black holes. Albert Einstein's theory of general relativity, which he published in 1915, revolutionized our understanding of gravity. The theory proposed that gravity is not a force between masses, but rather a curvature in the fabric of space-time caused by mass and energy. This new perspective allowed scientists to understand how extremely massive objects could warp space-time to the extent that even light could not escape their grasp. Einstein's equations predicted the existence of what would later be called black holes. Initially, these predictions were viewed as mathematical curiosities, but over time, further research and astronomical observations have shown that black holes are indeed a real phenomenon, confirming the accuracy of Einstein's theory. 14. The term black hole was coined by physicist John Archibald Wheeler in 1967. Although the concept of a black hole had been theorized long before, the term black hole was popularized by physicist John Archibald Wheeler in 1967. Prior to this, the objects were often referred to as collapsers or frozen stars. Wheeler's term, black hole, helped convey the idea that these objects were regions of space from which nothing, not even light, could escape. The term also reflected the mysterious and seemingly empty nature of black holes. While the term became widely accepted, it still evokes curiosity and intrigue as black holes continue to challenge our understanding of the universe and the laws of physics. 15. The size of a black hole is defined by its Schwarzschild radius, which is proportional to its mass. The size of a black hole, specifically the radius of its event horizon, is determined by the Schwarzschild radius, named after physicist Karl Schwarzschild, who derived the first exact solution to Einstein's equations for a non-rotating black hole. The Schwarzschild radius is directly proportional to the mass of the black hole. The larger the mass, the larger the Schwarzschild radius. For example, a black hole with the mass of the Sun would have a Schwarzschild radius of about 3 kilometers. A supermassive black hole with millions of solar masses would have an event horizon several million kilometers across. The Schwarzschild radius provides a useful way to calculate the size of the event horizon and is crucial for understanding the properties of black holes. 16. Black holes can spin. This is called rotating black holes or Kerr black holes. Not all black holes are static. Some spin rapidly. These rotating black holes are called Kerr black holes, after the physicist Roy P. Kerr, who first solved Einstein's equations for a rotating black hole in 1963. The rotation of a black hole affects the space-time around it, creating a region called the ergosphere, where objects can be dragged in the direction of the spin. The more massive the black hole, the faster it can rotate. The spin of a black hole is a crucial factor in determining its properties, such as how it emits energy and interacts with nearby matter. A rapidly spinning black hole can also extract energy from its accretion disk via a process known as the Penrose process, which involves splitting particles in the ergosphere. 17. Black holes can also have an electric charge, though most are considered neutral. While most black holes are considered electrically neutral, meaning they have no net charge, it is theoretically possible for a black hole to carry an electric charge. A charged black hole would interact with surrounding charged particles in a way that could affect its behavior, such as by attracting oppositely charged material or repelling similarly charged particles. However, the presence of a charge in a black hole is extremely rare in practice, as any significant charge would likely attract opposite charges and neutralize the black hole over time. Additionally, the interaction between charged black holes and their surroundings would lead to the emission of electromagnetic radiation, making them detectable. Nevertheless, the vast majority of known black holes are electrically neutral. 18. Time appears to slow down near the event horizon due to intense gravity. This is called time dilation. One of the most fascinating effects of a black hole is the extreme time dilation that occurs near its event horizon. According to Einstein's theory of general relativity, the stronger the gravitational field, the slower time passes relative to an observer farther away from the source of gravity. As an object approaches the event horizon of a black hole, the gravitational field becomes stronger and stronger, causing time to slow down dramatically. For an outside observer, an object falling into a black hole appears to freeze and fade as it gets closer to the event horizon. However, for the object itself, time would appear to pass normally. This effect is a direct consequence of the curvature of space-time near a black hole. 19. Inside a black hole's event horizon, all paths lead to the singularity. The event horizon of a black hole is the point beyond which nothing can escape, not even light. Once an object crosses this boundary, all of its possible paths lead inward toward the singularity, the point at the center of the black hole where gravity becomes infinitely strong and space-time curves to an extreme. The singularity is a region where the laws of physics, as we currently understand them, break down. The curvature of space-time becomes so extreme that classical concepts like distance, time, and even causality no longer apply. While we cannot observe the interior of a black hole directly, our understanding of physics suggests that anything entering the event horizon is inevitably drawn toward the singularity. 20. A singularity is a point of infinite density and zero volume. At the very center of a black hole lies the singularity, a point where matter is compressed to infinite density and occupies zero volume. The singularity is the endpoint of the collapse of the star that formed the black hole, where gravity becomes so intense that the laws of physics cease to function in the way we understand them. At this point, both space and time break down. The singularity is not something that can be observed directly, as it is hidden within the event horizon, but it is a mathematical prediction of Einstein's theory of general relativity. The infinite density and curvature of space-time at the singularity present one of the greatest challenges in physics, as current theories of gravity and quantum mechanics are unable to fully describe what happens in this extreme environment. 21. Black holes emit X-rays and gamma rays when they pull in matter from nearby stars. When a black hole pulls in matter from a nearby star or gas cloud, it forms an accretion disk around the event horizon. As the matter spirals inward, it is heated to extreme temperatures due to friction and gravitational forces, causing it to emit radiation across the electromagnetic spectrum. The inner regions of the accretion disk, which are closest to the black hole, can reach temperatures of millions of degrees, making them sources of X-rays and gamma rays. These high-energy emissions can be detected by space telescopes, allowing astronomers to study black holes and their accretion processes. This radiation is one of the key methods used to identify black holes in distant galaxies, as the black holes themselves are invisible. 22. The material falling into a black hole forms an accretion disk, which can get extremely hot and bright. The accretion disk is a swirling mass of gas, dust, and other matter that forms around a black hole as material is pulled toward it. This disk forms because the black hole's gravity causes the material to spiral inward. As the matter gets closer to the event horizon, it speeds up and heats up due to friction and gravitational forces, becoming extremely hot, often millions of degrees. This heating causes the accretion disk to emit intense radiation, including X-rays and ultraviolet light. In some cases, the disk can become so bright that it outshines the entire galaxy, making it one of the most visible features of an active black hole. The accretion disk also plays a critical role in the growth of the black hole, as it supplies the mass needed for the black hole to increase in size. 23. Supermassive black holes can have masses up to billions of times that of the Sun. Supermassive black holes, SMBHs, are the largest type of black holes, with masses ranging from millions to billions of times that of the Sun. These black holes are typically located at the centers of galaxies, including our own Milky Way. The exact mechanism of how SMBHs form is still a mystery, but it is believed that they may grow over billions of years by accumulating gas, dust, and even smaller black holes through mergers. The presence of these black holes at the centers of galaxies plays a crucial role in shaping the galaxy's structure and evolution. Some SMBHs are so massive that their gravitational pull influences the motion of stars and gas in the surrounding galaxy, often leading to active galactic nuclei, which are bright centers of galaxies due to intense radiation from the accretion disks. 24. Gravitational waves, first detected in 2015, are ripples in spacetime caused by black hole mergers. Gravitational waves are ripples in the fabric of spacetime caused by the acceleration of massive objects, such as when black holes merge. In 2015, scientists at the Laser Interferometer Gravitational Wave Observatory, LIGO, made the groundbreaking discovery of gravitational waves, which were produced by the merger of two black holes. The detection of these waves confirmed a major prediction of Einstein's theory of general relativity. When two black holes spiral toward each other and eventually merge, they release an enormous amount of energy in the form of gravitational waves, which travel across the universe. The ability to detect these waves opens a new window for studying black holes and the extreme physics that occur during their collisions. 25. Black holes can merge, creating larger black holes and releasing massive amounts of energy. Black holes are capable of merging with one another, resulting in the formation of an even larger black hole. When two black holes in a binary system get close enough, their gravitational pull causes them to spiral toward each other. As they get closer, they emit gravitational waves, which carry away energy, causing the black holes to slowly lose momentum and eventually collide. When the black holes merge, they release an enormous amount of energy, often in the form of gravitational waves. The resulting black hole is typically more massive than either of the original black holes. The energy released during a black hole merger is so intense that it can outshine the combined light of billions of stars for a brief period, making these events detectable across vast distances. 26. It is believed that the Big Bang may have created small black holes in the early universe. The Big Bang, which marked the beginning of the universe about 13.8 billion years ago, could have created tiny black holes, known as primordial black holes, in its aftermath. These black holes would have formed from high-density fluctuations in the early universe, where regions of space were dense enough to collapse into black holes. primordial black holes would have been much smaller than stellar mass black holes, with masses ranging from tiny to several times the mass of the Sun. While no primordial black holes have been directly detected, they remain a theoretical possibility. Some scientists believe that they could account for dark matter, the mysterious substance that makes up most of the mass in the universe but does not emit light or radiation. 27. Black holes are invisible in the traditional sense, but can be studied by their effects on nearby matter. One of the most intriguing aspects of black holes is that they are invisible. No light or radiation can escape from them. However, they can be studied indirectly by observing their effects on the matter around them. For example, when a black hole is in a binary system with a companion star, the gravitational influence of the black hole causes the star to move in a way that can be detected. Similarly, when a black hole pulls in gas and dust from a nearby cloud, the resulting accretion disk emits radiation, including X-rays, that can be detected by telescopes. In some cases, black holes can also produce powerful jets of particles, which can be observed as they shoot away from the black hole's poles. These indirect observations provide valuable information about black holes and their behavior. 28. There are black holes with masses less than that of the Sun, known as micro-black holes. While most black holes are stellar mass or supermassive, it is theorized that much smaller black holes, called micro-black holes, could exist. These black holes would have masses significantly less than that of the Sun, possibly as small as the mass of an asteroid. Micro-black holes could form through high-energy collisions or quantum fluctuations in the early universe. Although no micro-black holes have been observed, their existence is predicted by certain models of quantum gravity. In theory, these small black holes would have much smaller event horizons and would rapidly evaporate due to Hawking radiation, emitting particles and energy before disappearing completely. Their discovery would provide insights into quantum mechanics and the nature of gravity at very small scales. 29. Some black holes may evaporate over time due to a phenomenon called Hawking radiation. Black holes are not necessarily permanent. According to theoretical physicist Stephen Hawking, black holes can slowly lose mass and energy through a process called Hawking radiation. This phenomenon occurs because of quantum mechanical effects near the event horizon, where particle-antiparticle pairs are constantly being created and annihilated. Occasionally, one of the particles will escape while the other is absorbed by the black hole. The particle that escapes carries away energy, causing the black hole to lose mass over time. Over incredibly long periods, this process could lead to the evaporation of a black hole. The radiation itself is very weak for large black holes, so it is not detectable with current technology, but for smaller black holes, it could be more significant. 30. The process of Hawking radiation was proposed by physicist Stephen Hawking in 1974. In 1974, physicist Stephen Hawking proposed a groundbreaking theory that suggested black holes could emit radiation. This radiation, now known as Hawking radiation, arises due to quantum effects near the event horizon. According to quantum mechanics, pairs of particles are constantly being created and annihilated near the event horizon. Occasionally, one of these particles will escape into space, while the other is captured by the black hole. The escaping particle carries away energy, which causes the black hole to lose mass over time. This process implies that black holes can slowly evaporate over very long timescales. The discovery of Hawking radiation was revolutionary because it combined principles of quantum mechanics, general relativity, and thermodynamics, leading to the concept of black holes having a finite lifetime. 31. The no-hair theorem suggests that black holes only have three observable characteristics: mass, charge, and spin. The no-hair theorem, proposed by physicists John Archibald Wheeler and others, suggests that black holes are incredibly simple objects. According to the theorem, black holes can only be described by three observable properties: mass, charge, and spin. This means that no other distinguishing characteristics, such as the material that formed the black hole, can be observed from outside the event horizon. Once a black hole is formed, all information about the original star or object that collapsed into it is erased from the outside universe. The theorem is based on the idea that black holes are featureless beyond their mass, charge, and spin, making them simple yet mysterious objects in space. 32. Black holes are not a hole in space, but a concentration of mass. A common misconception is that black holes are holes or empty spaces in the universe, but in reality, they are regions of extremely dense matter. A black hole forms when a massive star or object collapses under its own gravity, concentrating an enormous amount of mass into a very small area. This concentration of mass warps space-time to an extreme degree, creating a gravitational field so strong that nothing, not even light, can escape it. The event horizon marks the boundary around the black hole. But inside this region, the mass continues to concentrate at a point known as the singularity. Thus, rather than being a hole, a black hole is a massive compact object with intense gravitational forces. 33. Stellar black holes typically have masses between 3 and 10 times that of the Sun. Stellar black holes are typically formed when massive stars collapse at the end of their life cycles. The mass of a stellar black hole usually ranges from about 3 to 10 times the mass of our Sun. These black holes form when a star with enough mass, usually 20 times or more the mass of the Sun, exhausts its nuclear fuel and undergoes a supernova explosion. The core that remains after the explosion becomes dense enough to collapse into a black hole. The exact mass of a stellar black hole depends on the star's initial mass and the processes involved during the collapse. These black holes are often found in binary systems, where they interact with a companion star. 34. Intermediate black holes are thought to exist in the range of 100 to 1,000 solar masses. Intermediate black holes, IMBHs, are black holes with masses between those of stellar mass black holes, 3-10 solar masses, and supermassive black holes, millions to billions of solar masses. Theoretical models suggest that IMBH could have masses in the range of 100 to 1,000 solar masses, but their existence is still a subject of ongoing research. These black holes might form in dense stellar clusters or through the merging of smaller black holes. Some astronomers believe that IMBHs could be responsible for the formation of supermassive black holes over time, as they could merge and grow into much larger black holes. Although no intermediate black holes have been definitively detected, a few candidates have been found in certain stellar environments. 35. It is still unknown how supermassive black holes form, but they may grow by merging with other black holes. The formation of supermassive black holes, SMBHs, which can have masses ranging from millions to billions of times that of the Sun, is still a major mystery in astrophysics. While the formation of stellar mass black holes is relatively well understood, forming from the collapse of massive stars, the origin of SMBHs is unclear. One leading theory is that they may have formed from the merging of smaller black holes, or from the accretion of large amounts of gas and dust over billions of years. Another possibility is that SMBH could have grown from seed black holes formed in the early universe, which accumulated mass over time through mergers with other black holes and by pulling in gas from their surroundings. Understanding the formation of SMBHs is crucial for understanding the evolution of galaxies and the role black holes play in shaping the universe. 36. Supermassive black holes are found at the centers of most galaxies, and their growth is linked to galaxy evolution. Supermassive black holes, SMBHs, are thought to reside at the centers of nearly all large galaxies, including our own Milky Way. These black holes can have masses ranging from millions to billions of times that of the Sun. The presence of a supermassive black hole at the center of a galaxy is believed to be a key factor in the galaxy's formation and evolution. The black hole's gravity can influence the motion of stars and gas in the galaxy, and its growth can regulate the rate of star formation by controlling the supply of gas. In some cases, the energy released by an active black hole, one that is rapidly accreting matter, can blow gas out of the galaxy, preventing new stars from forming. Thus, the growth of SMBHs is closely tied to the evolution of galaxies. 37. A black hole's size, Schwarzschild radius, is directly proportional to its mass. The Schwarzschild radius is the distance from the center of a black hole to its event horizon, and it is directly proportional to the black hole's mass. The larger the mass of the black hole, the larger the Schwarzschild radius. For example, a black hole with a mass equivalent to the Sun has a Schwarzschild radius of about 3 kilometers. In contrast, a supermassive black hole, which can have a mass millions or even billions of times that of the Sun, can have a Schwarzschild radius that is several million kilometers across. The Schwarzschild radius provides a simple way to estimate the size of a black hole's event horizon based on its mass, helping scientists understand the relationship between a black hole's mass and the space-time curvature it produces. 38. The event horizon is not a solid surface, but rather a point of no return. The event horizon of a black hole is often misunderstood as a physical surface, but it is not a solid boundary. Instead, it is the point at which the escape velocity from the black hole exceeds the speed of light. Once an object crosses the event horizon, it is effectively trapped inside the black hole, as no force can overcome the black hole's gravitational pull to escape. The event horizon is the point of no return, and once anything crosses it, it can never be observed again. Despite the fact that the event horizon has no physical structure, it is a crucial concept in understanding the behavior of black holes, as it defines the limit beyond which nothing can escape the black hole's grasp. 39. Black holes can cause a phenomenon known as gravitational lensing, where light is bent around them. Black holes have such a strong gravitational field that they can bend light around them, creating a phenomenon known as gravitational lensing. This occurs because gravity affects the curvature of space-time, and light follows the curved paths dictated by space-time. When light from a distant object, such as a star or galaxy, passes near a black hole, the intense gravity of the black hole can bend the light, magnifying or distorting the image of the background object. In some cases, gravitational lensing can create multiple images of the same object, known as an Einstein ring, when the black hole is perfectly aligned with the observer. Gravitational lensing provides a powerful tool for studying black holes and the distribution of matter in the universe. 40. The famous spaghettification effect happens when an object falls into a black hole and gets stretched by tidal forces. The phenomenon known as spaghettification occurs when an object is stretched by the immense tidal forces near a black hole. As an object approaches the event horizon, the difference in gravitational pull between its near side and far side becomes extreme. The side closest to the black hole experiences a much stronger gravitational force, while the far side experiences a weaker pull. This difference in forces stretches the object into a long, thin shape, resembling spaghetti as it is pulled toward the black hole. The closer the object gets to the event horizon, the more intense the tidal forces become, eventually tearing the object apart. Spaghettification is a dramatic consequence of the immense gravitational forces near black holes. 41. The first image of a black hole was captured in 2019 by the Event Horizon Telescope. In April 2019, the Event Horizon Telescope (EHT) collaboration released the first ever image of a black hole. This historic image was of the supermassive black hole at the center of the galaxy M87, located about 55 million light-years from Earth. The EHT is a network of radio telescopes spread across the globe, effectively creating a planet-sized telescope. The image shows a glowing ring of light, with the center appearing dark. This is the shadow of the black hole itself. The light around the black hole comes from the heated gas in the accretion disk. This achievement marked a major milestone in the study of black holes and provided direct visual evidence for their existence, confirming many theoretical predictions. 42. Black holes are one of the most extreme environments in the universe. Black holes represent some of the most extreme environments in the universe due to their immense gravitational forces and the breakdown of known physical laws. The environment near a black hole is characterized by ultra-high gravity, intense radiation from the accretion disk, and the potential for violent interactions with nearby objects. At the center of a black hole, within the singularity, the density and gravity are so high that general relativity and quantum mechanics, two cornerstone theories of physics, fail to describe the phenomena accurately. These extreme conditions provide researchers with an opportunity to test the limits of both theories and explore the mysteries of space-time, gravity, and quantum mechanics. 43. The discovery of gravitational waves from black hole mergers was one of the most significant scientific breakthroughs of the 21st century. The discovery of gravitational waves from black hole mergers in 2015 was a groundbreaking event in physics. Scientists at the Laser Interferometer Gravitational Wave Observatory, LIGO, detected ripples in spacetime caused by the collision of two black holes. This confirmed a key prediction of Einstein's theory of general relativity and opened a new field of astronomy. Gravitational waves carry information about the most energetic events in the universe, such as black hole mergers and neutron star collisions. These waves travel at the speed of light and can be detected on Earth, providing a new way to observe the cosmos and explore phenomena that were previously invisible to traditional telescopes. 44. A rotating black hole, Kerr black hole, can allow matter to orbit it in stable orbits, called the ergosphere. A rotating black hole, also known as a Kerr black hole, is a black hole that has angular momentum, meaning it spins around its axis. The rotation of the black hole affects the space-time around it, dragging space-time in the direction of the black hole's spin. a phenomenon known as frame dragging. This creates a region outside the event horizon called the ergosphere, where matter can orbit the black hole in stable orbits. In the ergosphere, it is still possible for objects to escape, but they must gain energy by interacting with the black hole. In some cases, particles can be accelerated to high velocities, leading to the emission of powerful jets of radiation from the black hole's poles. 45. The ergosphere is the region outside the event horizon where space-time is dragged along by the rotating black hole. The ergosphere is a unique region around a rotating black hole where space-time itself is twisted by the black hole's rotation. This region lies outside the event horizon, but within the black hole's gravitational influence. In the ergosphere, the intense rotation of the black hole causes space-time to be dragged along in the direction of the spin. This effect is known as frame dragging. As a result, objects within the ergosphere cannot remain stationary relative to distant observers. They must move in the direction of the black hole's spin. The ergosphere also allows for a phenomenon known as the Penrose process, where energy can be extracted from the black hole by splitting particles in the ergosphere. 46. Some black holes are found in the center of globular clusters, which are dense groups of stars. Black holes are not only found at the centers of galaxies, but also in other dense stellar environments, such as globular clusters. A globular cluster is a tightly bound group of hundreds of thousands to millions of stars, all packed into a relatively small region of space. The high stellar density and gravitational interactions within these clusters can lead to the formation of stellar mass black holes. In some cases, these black holes can grow by accreting matter from their surroundings or by merging with other black holes. Evidence of black holes in globular clusters is often detected through their effects on nearby stars, such as by observing the motion of stars that are being influenced by the black hole's gravity. 47. There are theories suggesting the existence of primordial black holes formed in the early universe. Primordial black holes are a theoretical type of black hole that could have formed in the very early universe, shortly after the Big Bang. Unlike stellar mass black holes, which form from the collapse of massive stars, primordial black holes would have formed from high-density fluctuations in the early universe, when the universe was still very hot and dense. These fluctuations could have caused certain regions of space to collapse into black holes. Primordial black holes would have a wide range of possible sizes, from very small, with masses less than that of the Sun, to much larger ones. Some scientists speculate that primordial black holes could be a source of dark matter, though no primordial black holes have been detected yet. 48. In theory, black holes could be portals to other parts of the universe, but this is highly speculative. The idea that black holes could serve as portals to other parts of the universe, or even other universes, is a fascinating theoretical possibility, though it remains highly speculative. One popular theory is that black holes might be connected to wormholes, hypothetical tunnels through space-time that could provide shortcuts between distant regions of the universe. If such wormholes exist, a black hole might serve as the entrance to one. However, no evidence has been found to support the existence of wormholes, and the intense gravity near the event horizon would likely destroy any matter attempting to pass through. While this concept is popular in science fiction, it has not been proven or widely accepted in the scientific community. 49. The event horizon marks the limit beyond which nothing can escape, but it doesn't mean there's a physical surface. The event horizon of a black hole is often misunderstood as a physical surface or edge, but in reality, it is not a solid boundary. Instead, it is the point at which the escape velocity from the black hole exceeds the speed of light, meaning that nothing can escape from within the event horizon, including light. The event horizon is the point of no return, beyond which anything that enters is doomed to be pulled toward the singularity at the black hole's center. However, there is no actual physical surface at the event horizon. It is a mathematical boundary defined by the behavior of space-time and gravity, not a tangible, solid surface that can be observed. 50. The energy released during black hole mergers can outshine entire galaxies. When two black holes merge, they release an immense amount of energy in the form of gravitational waves, which can travel across the universe. These mergers are some of the most energetic events in the universe and can release more energy in a fraction of a second than our entire galaxy emits in billions of years. This massive release of energy is not in the form of visible light, but rather in the form of gravitational waves, which are detected by instruments like LIGO. During the merger, the resulting black hole can also emit high-energy radiation from the accretion disk, sometimes making it appear brighter than entire galaxies for a brief period. These energetic events provide valuable insights into the behavior of black holes and the fundamental physics of gravity. 51. In binary systems, a black hole can pull matter from its companion star, forming an X-ray binary. In binary systems, one of the stars may be a black hole. As the black hole orbits its companion star, it can pull gas and material from the star's outer layers, forming an accretion disk around the black hole. This process is known as mass transfer, and it results in the formation of an X-ray binary system. The material in the accretion disk gets heated to extremely high temperatures, emitting X-rays and sometimes even gamma rays as it spirals inward toward the black hole. These X-ray emissions can be detected by telescopes and serve as one of the primary methods of discovering black holes in binary systems. The interaction between the black hole and its companion star can also cause the black hole to gain mass, allowing it to grow over time. 52. The physics of black holes requires understanding quantum mechanics and general relativity simultaneously. Black holes are one of the few places in the universe where both quantum mechanics and general relativity must be considered together. General relativity, developed by Einstein, describes the gravitational effects of massive objects and how space-time is curved by their mass. Quantum mechanics, on the other hand, deals with the behavior of particles at extremely small scales. While both theories are well tested in their respective domains, they are not compatible in their current forms when it comes to black holes. At the singularity, where gravity is extremely strong and space-time is warped to infinite density, quantum effects are expected to play a critical role. Understanding black holes fully requires a theory of quantum gravity, which remains one of the biggest challenges in modern physics. 53. Black holes can sometimes emit jets of high-energy particles, which can extend for millions of light years. Some black holes, particularly supermassive black holes at the centers of active galaxies, are capable of emitting powerful jets of high-energy particles. These jets are launched along the rotational axis of the black hole and can extend for millions of light years into space. The exact mechanism behind the formation of these jets is still not fully understood. but they are believed to be the result of the interaction between the black hole's magnetic field and the matter in the accretion disk. As the material spirals toward the black hole, it can be channeled into narrow beams of radiation and particles, which are ejected at nearly the speed of light. These jets can have a significant impact on the surrounding galaxy, sometimes regulating star formation or causing gas to be expelled from the galaxy. 54. Matter falling into a black hole is heated to extreme temperatures, often reaching millions of degrees. As matter falls toward a black hole, it is pulled into an accretion disk, a swirling mass of gas and debris that heats up due to friction and intense gravitational forces. The closer the matter gets to the event horizon, the more it accelerates and the hotter it becomes. In some cases, the temperatures in the inner regions of the accretion disk can reach millions of degrees. This extreme heat causes the material to emit high-energy radiation, including X-rays and ultraviolet light. The process of heating up matter before it falls into the black hole makes the black hole detectable through the radiation emitted by the accretion disk. These intense temperatures also help explain the powerful radiation jets emitted by some black holes. 55. The largest black holes found are located in the centers of massive galaxies. Supermassive black holes, which can have masses ranging from millions to billions of times that of the Sun, are typically found at the centers of massive galaxies. These black holes are thought to play a crucial role in the formation and evolution of galaxies. Their enormous gravitational pull influences the motion of stars and gas in their galaxies, and their growth is often linked to the overall growth of the galaxy. The largest known black holes, like the one in the galaxy M87, have been detected by observing the motions of stars and gas around them, as well as by studying the radiation emitted from the accretion disk and jets. These black holes can reach sizes large enough to dominate the gravitational environment of their host galaxies. 56. Black holes don't suck everything in their surroundings unless the objects are close enough. A common misconception about black holes is that they suck everything around them. In reality, black holes only exert a strong gravitational pull on objects that come too close. If a star, planet, or any other object is far enough from a black hole, it can safely orbit the black hole, just as Earth orbits the Sun. The sucking effect only occurs when an object passes too close to the event horizon. At this point, the object's escape velocity exceeds the speed of light, and it becomes trapped. Thus, black holes do not act as cosmic vacuum cleaners, but rather as extremely strong gravitational centers that only affect objects within their immediate vicinity. 57. While black holes do not technically suck matter in a vacuum, they can strongly influence the motion of nearby stars and gas. Black holes have a powerful gravitational influence on their surroundings, but this influence is not limited to directly pulling in matter. The gravity of a black hole can cause nearby stars and gas to move in unusual ways. For example, in a binary system with a black hole and a companion star, the gravitational pull from the black hole will cause the star to orbit in an elliptical or irregular pattern. In some cases, this can lead to the star being stripped of its outer layers, which are then drawn into the black hole. Similarly, gas clouds near a black hole can be distorted and pulled in, forming accretion disks and emitting radiation as they spiral toward the event horizon. Black holes can thus have a major impact on the dynamics of the material in their vicinity, even if they are not directly pulling in everything around them. 58. The information paradox refers to the unresolved question of what happens to information that falls into a black hole. The information paradox is one of the biggest unresolved questions in physics. According to the principles of quantum mechanics, information about the state of a system, such as the properties of particles, cannot be lost. However, when information falls into a black hole, it appears to be lost to the outside world, as no signals can escape from within the event horizon. This creates a conflict between quantum mechanics and general relativity. Some scientists suggest that the information might be encoded in the radiation emitted by the black hole, Hawking radiation, or that it could be stored on the event horizon itself in a manner known as holography. Resolving the information paradox is crucial for understanding the true nature of black holes and the relationship between quantum mechanics and gravity. 59. Black holes can be surrounded by a halo of hot ionized gas. Black holes, especially supermassive ones at the centers of galaxies, are often surrounded by a halo of hot ionized gas. This gas is typically formed from the material being pulled into the black hole from the surrounding space. As the gas spirals toward the black hole, it forms an accretion disk and is heated to extremely high temperatures due to friction and gravitational forces. This hot gas emits X-rays and other forms of radiation, which can be detected by telescopes. The gas in the halo is often highly ionized, meaning that the atoms in the gas have been stripped of their electrons by the intense radiation and heat. This hot, ionized gas can extend for vast distances around the black hole and can interact with the surrounding galaxy, affecting star formation and the overall dynamics of the system. 60. Many stars in the Milky Way are in binary systems with black holes. The Milky Way galaxy contains many binary systems where one of the objects is a black hole. In these systems, a normal star orbits a black hole, with the black hole's strong gravity pulling material from the star. This material forms an accretion disk around the black hole, and as it falls in, it is heated to extremely high temperatures, emitting X-rays and other radiation. The interaction between the black hole and its companion star is a common way to detect the presence of a black hole, as the X-ray emissions from the accretion disk can be observed by space telescopes. Binary systems with black holes are valuable for studying the properties of black holes, such as their mass and spin, and provide insights into how black holes grow and interact with their environments. 61. The inner edge of an accretion disk is often very close to the event horizon of a black hole. The accretion disk around a black hole consists of gas and debris that spirals toward the event horizon. The inner edge of this disk lies at a very specific distance from the black hole. For a non-rotating black hole, the innermost stable orbit for matter is typically about 3 times the Schwarzschild radius, the radius of the event horizon. For rotating black holes, Kerr black holes, this distance can be closer due to the effects of the black hole's spin. The matter in the inner regions of the accretion disk becomes incredibly hot and dense as it accelerates toward the event horizon. As it heats up, it emits high-energy radiation, including X-rays, making the accretion disk one of the brightest features around a black hole. The inner edge of the accretion disk marks the point beyond which matter can no longer maintain stable orbits and inevitably falls into the black hole. 62. Stellar black holes are typically formed by the collapse of massive stars. Stellar black holes are formed when massive stars, typically those with more than 20 times the mass of the Sun, reach the end of their life cycle. After exhausting their nuclear fuel, these stars can no longer support themselves against the force of gravity, and their cores collapse inward. If the collapsing core is heavy enough, it compresses into a singularity, forming a black hole. The outer layers of the star are ejected in a violent supernova explosion, leaving behind a dense remnant in the form of a black hole. Stellar black holes usually have masses between 3 and 10 times the mass of the Sun. These black holes are scattered across the universe and can be found in binary systems where they interact with a companion star. 63. The density of a black hole is theoretically infinite at the singularity. At the center of a black hole lies the singularity, where the mass of the black hole is concentrated into a point of infinite density and zero volume. This means that the gravitational forces at the singularity are so intense that space-time itself curves infinitely, and our understanding of physics breaks down. The concept of infinite density is difficult to reconcile with the laws of physics as we know them. The singularity is a prediction of general relativity, but quantum mechanics suggests that this extreme condition might not be physically possible, indicating that a complete theory of quantum gravity is needed to explain what happens at this point. The singularity lies within the event horizon, so it cannot be directly observed, but its presence is a fundamental aspect of black hole theory. 64. Black holes can act as powerful sources of radiation as they accrete material. When a black hole pulls in material from a nearby star or gas cloud, the process of accretion can produce powerful radiation. As the matter spirals inward toward the black hole, it forms an accretion disk, which is heated to incredibly high temperatures due to friction and gravitational forces. This causes the material to emit electromagnetic radiation, including X-rays, ultraviolet, and sometimes even gamma rays. The closer the material gets to the event horizon, the hotter and brighter it becomes. The radiation emitted by the accretion disk can be so intense that it outshines the rest of the galaxy in some cases, turning the black hole into an active galactic nucleus, AGN. This process of radiation emission provides the key method for detecting black holes in distant galaxies. 65. One theory about the formation of supermassive black holes suggests that they grew from the merger of smaller black holes. One leading theory about the formation of supermassive black holes, SMBHs, at the centers of galaxies is that they may have formed from the merger of smaller black holes. In the early universe, smaller black holes, each formed by the collapse of massive stars, could have merged over time due to gravitational interactions. These mergers would have caused the black holes to grow in size, eventually forming a supermassive black hole. This theory is supported by the observation of large black holes in the centers of galaxies that appear to have grown over billions of years. The merger process might still be ongoing today, as smaller black holes continue to collide and merge, contributing to the growth of SMBHs. 66. A black hole's gravitational pull is so strong that it can even pull light from nearby objects, causing gravitational redshift. Black holes have an extremely strong gravitational field that affects the path of light. As light passes near a black hole, the intense gravity bends the light, a phenomenon known as gravitational lensing. However, if light is emitted from an object that is very close to the black hole, the gravitational pull will also cause the light to lose energy, leading to a shift toward longer wavelengths. known as gravitational redshift. This means that the light appears redder as it loses energy while escaping from the black hole's gravitational influence. The closer the light source is to the black hole, the greater the redshift. Gravitational redshift provides important information about the properties of black holes and the structure of space-time near them. 67. The inner structure of a black hole, including the singularity, is still not fully understood. While the basic theory of black holes is well established, the exact nature of their inner structure remains a subject of intense research. The singularity at the center of a black hole is predicted to be a point of infinite density, where space-time curvature becomes infinite. However, the laws of physics break down at this extreme, and we currently have no complete theory to describe the behavior of matter and energy under such conditions. General relativity predicts the existence of the singularity, but it does not explain how quantum effects might alter this picture. Understanding the inner workings of a black hole will require a theory of quantum gravity that combines general relativity and quantum mechanics, two fundamental but incompatible theories of physics. 68. Black holes are detected indirectly by observing the motion of nearby objects or by the radiation they emit. Black holes cannot be directly observed because no light can escape from them. However, astronomers can detect black holes by observing their effects on nearby objects. For example, in binary systems, a black hole's gravity can cause a companion star to move in unusual orbits. By studying the motion of the star and applying Kepler's laws of motion, astronomers can estimate the mass of the unseen black hole. Additionally, the radiation emitted from the accretion disk of a black hole as it pulls in gas or material from a companion star can be detected by space telescopes. X-ray emissions from the accretion disk, along with gravitational wave signals from black hole mergers, provide indirect evidence of black holes in the universe. 69. There may be many smaller black holes scattered throughout the universe, too faint to detect. While supermassive and stellar mass black holes are relatively easy to detect by their effects on nearby stars and gas, many smaller black holes are thought to exist throughout the universe, but they are much harder to observe. These smaller black holes, known as intermediate or micro black holes, might be too faint or distant to detect with current technology. Intermediate black holes, with masses between 100 and 1,000 times that of the Sun, are especially elusive. These smaller black holes could be scattered throughout our galaxy and others, hiding in the midst of other stellar objects. Theoretical models suggest that black holes with masses below the typical stellar range could exist, but their detection requires sensitive instruments and new methods of observation. 70. Black holes might be able to power active galactic nuclei by accreting matter at a high rate. Active galactic nuclei, AGN, are the bright centers of galaxies, often emitting large amounts of radiation, including X-rays and gamma rays. Many AGNs are powered by the presence of a supermassive black hole at the center of the galaxy. The black hole's gravitational pull causes surrounding gas and dust to fall toward it, forming an accretion disk that heats up to extremely high temperatures, producing intense radiation. As the black hole rapidly accretes material, it can release enormous amounts of energy, powering the AGN. Some AGNs can outshine their entire host galaxy due to the energy released from the black hole's accretion process. This makes supermassive black holes a key element in the understanding of galaxy evolution and the role black holes play in the larger cosmic environment. 71. The process of black hole evaporation through Hawking radiation is incredibly slow for large black holes. According to Stephen Hawking's theory of black hole evaporation, black holes are not completely black, but instead slowly lose mass over time through a process known as Hawking radiation. This radiation arises from quantum effects near the event horizon, where particle-antiparticle pairs are spontaneously created. One of these particles can fall into the black hole, while the other escapes, carrying away energy. This process causes the black hole to lose mass and shrink gradually. However, for large black holes, like those with masses several times that of the Sun, this evaporation is incredibly slow, taking longer than the current age of the universe. For smaller black holes, the process would be faster, and they could evaporate completely over time. But the evaporation of supermassive black holes is not significant on human timescales. 72. Black holes have a profound effect on the fabric of space-time, bending it to extremes. Black holes are known for their ability to warp space-time to extreme levels due to their incredibly strong gravitational fields. According to Einstein's theory of general relativity, mass causes space-time to curve, and black holes are the ultimate example of this effect. The gravity near a black hole is so strong that it stretches space-time, causing light to bend around it, and even time to slow down near the event horizon. This warping of space-time leads to some fascinating phenomena, such as gravitational lensing, where light from distant stars or galaxies is distorted as it passes near the black hole, and time dilation, where time appears to slow down for an object approaching the event horizon. 73. The center of our galaxy contains a supermassive black hole called Sagittarius A. The center of the Milky Way galaxy is home to a supermassive black hole named Sagittarius AI. With a mass of approximately 4 million times that of the Sun, this black hole lies about 26,000 light-years away from Earth. Although it is not actively consuming large amounts of material at the moment, Sagittarius A's style plays a crucial role in the dynamics of the Milky Way's central region. Scientists have studied the motion of stars near the center of the galaxy, and their behavior suggests the presence of this supermassive black hole. Observing Sagittarius A helps astronomers understand the behavior of supermassive black holes and their influence on galaxy formation and evolution. 74. The first black hole detection was based on observing the motion of a star in a binary system. The first evidence for the existence of a black hole came in the 1970s, when astronomers observed the motion of a companion star in a binary system. The system, called Cygnus X1, was discovered to contain a massive unseen object that was pulling material from its companion star. The gravitational influence of this object caused the companion star to orbit in an unusual way, suggesting the presence of an object with a mass several times that of the Sun, but invisible. This led to the conclusion that the object was a black hole. This discovery marked the first confirmation of black holes' existence, and since then, many more have been detected using similar methods, such as observing the behavior of nearby stars or detecting X-ray emissions from accretion disks. 75. Some black holes are thought to be responsible for the creation of powerful jets of particles. Certain black holes, particularly those that are actively accreting matter, can produce powerful jets of particles that shoot out from their poles at nearly the speed of light. These jets are formed when material in the accretion disk is accelerated by the intense magnetic fields around the black hole. As the material spirals toward the event horizon, some of it is funneled along the black hole's rotation axis, forming narrow beams of particles. These jets can extend for thousands or even millions of light years and can be detected in distant galaxies. The jets are a significant aspect of active galactic nuclei, AGN, and quasars, where the energy emitted by the black hole's accretion process outshines the rest of the galaxy. 76. The discovery of gravitational waves from black hole mergers opened a new way of observing the universe. Gravitational waves, first detected in 2015 by the Laser Interferometer Gravitational Wave Observatory, LIGO, are ripples in space-time caused by the acceleration of massive objects, such as black hole mergers. The discovery of these waves confirmed a major prediction of Einstein's theory of general relativity and provided a new way to observe the universe. Unlike traditional light-based telescopes, which observe electromagnetic radiation, gravitational wave detectors can detect the ripples caused by black hole collisions and other violent cosmic events. Gravitational waves allow scientists to study the properties of black holes and other celestial objects in ways that were previously impossible, opening up a new frontier in astrophysics. 77. The spinning of black holes can lead to the formation of relativistic jets. When black holes spin, they drag space-time with them, an effect known as frame dragging or the lens-thirring effect. This spinning black hole can accelerate nearby particles to relativistic speeds, forming powerful jets of high-energy particles. These jets can be emitted along the black hole's rotational axis and can extend vast distances into space. The magnetic fields around a rotating black hole play a crucial role in the formation of these jets. The jets are often seen in active galactic nuclei, where a supermassive black hole is actively accreting matter. The energy emitted in the form of these jets can outshine entire galaxies, making black holes some of the most energetic objects in the universe. 78. The exact size of a black hole can be determined by measuring the motion of nearby objects. The size of a black hole is defined by its Schwarzschild radius, which is the radius of the event horizon. While we cannot directly observe the event horizon, astronomers can determine the size of a black hole by observing the motion of nearby objects, such as stars or gas clouds. The motion of these objects is influenced by the black hole's gravity. By studying the orbits of nearby stars or the dynamics of an accretion disk, astronomers can estimate the mass of the black hole. Once the mass is determined, they can calculate the Schwarzschild radius and thus the size of the black hole's event horizon. This method has been used to measure the mass and size of black holes in various systems. 79. Some black holes are thought to be formed by the collapse of large gas clouds rather than stars. While most black holes are formed from the collapse of massive stars, it is also theorized that some black holes, particularly supermassive ones, could form from the collapse of large gas clouds. In the early universe, dense clouds of gas could have collapsed under their own gravity, forming black holes. These gas clouds may have been able to collapse directly into a black hole without going through the typical process of stellar evolution. This theory suggests that supermassive black holes could have formed early in the universe, possibly within the first few 100 million years after the Big Bang. Understanding how these black holes formed is a major area of research in astrophysics. 80. The formation and growth of supermassive black holes are tied to the evolution of galaxies. Supermassive black holes, SMBHs, are thought to play a central role in the evolution of galaxies. These black holes are typically located at the centers of galaxies, and their formation and growth are closely linked to the processes that shape galaxies. As SMBHs accrete matter and grow over billions of years, they can influence the surrounding galaxy by regulating star formation, expelling gas, and driving the motion of stars. In some cases, the radiation and winds produced by an active black hole can heat or expel gas from the galaxy, suppressing star formation. The growth of supermassive black holes is thought to be intertwined with the formation of galaxies, with both influencing each other's evolution over cosmic timescales. 81. Black holes are thought to be able to shrink over time by losing mass through Hawking radiation. As proposed by physicist Stephen Hawking, black holes slowly lose mass over time through a process known as Hawking radiation. This phenomenon arises due to quantum mechanical effects near the event horizon. Particle-antiparticle pairs are created near the event horizon, and one of the particles may fall into the black hole while the other escapes, carrying away energy. This gradual loss of mass causes the black hole to shrink over time. For most black holes, this process is incredibly slow, especially for supermassive black holes. However, over incredibly long timescales, this evaporation could lead to the eventual disappearance of the black hole. For smaller black holes, the process of evaporation would be much faster, possibly leading to their complete disappearance in a much shorter time. 82. Black holes are a key area of research in modern astrophysics and cosmology. Black holes are one of the most fascinating and mysterious objects in the universe, and they play a crucial role in modern astrophysics and cosmology. Research into black holes allows scientists to study extreme conditions of gravity, space-time, and matter, which cannot be replicated on Earth. The study of black holes helps researchers test the limits of Einstein's theory of general relativity, especially in environments where space-time is curved to an extreme degree. Additionally, understanding black holes is essential for comprehending the formation and evolution of galaxies, as well as the overall structure of the universe. Current black hole research includes the study of gravitational waves, the behavior of matter near event horizons, and the search for quantum gravity. 83. Black holes are detected indirectly by observing their effects on nearby stars or gas. Since black holes cannot be observed directly due to their lack of light, they are typically detected by observing their effects on nearby objects, such as stars or gas. In binary systems, for instance, a black hole's gravity can cause a companion star to orbit in an unusual manner, and by measuring the motion of this star, astronomers can infer the presence of the black hole. Similarly, when a black hole pulls gas from a nearby cloud, the material forms an accretion disk, which emits radiation due to the intense friction as the material spirals inward. This radiation, including X-rays and gamma rays, can be detected by telescopes, providing evidence of the black hole's existence. 84. The intense gravity near a black hole can distort the fabric of space-time, creating gravitational lensing. The intense gravitational field of a black hole can bend light from distant objects due to the warping of space-time. This effect is known as gravitational lensing. Light passing near a black hole is bent around it, and depending on the alignment of the observer, this can create multiple images or even a ring of light around the black hole, known as an Einstein ring. Gravitational lensing allows scientists to observe objects behind black holes that would otherwise be hidden, providing a way to study the mass distribution around black holes. The bending of light also helps researchers understand the properties of space-time near black holes, providing insight into their structure and the extreme gravitational effects they cause. 85. The exact nature of a black hole's singularity is still unknown. While black holes are well understood in many ways, the exact nature of the singularity at their center remains a mystery. The singularity is a point where space-time curvature becomes infinite and the laws of physics break down. In classical general relativity, the singularity is a point of infinite density, with all the mass of the black hole concentrated in an infinitely small space. However, quantum mechanics suggests that such infinities may not be physically possible, and a quantum theory of gravity is needed to fully describe the conditions at the singularity. The study of black holes and singularities remains one of the most significant challenges in modern physics, as scientists seek to reconcile general relativity and quantum mechanics. 86. In theory, black holes might be able to power active galactic nuclei, AGN. Active galactic nuclei, AGN, are bright, energetic regions at the centers of some galaxies, often emitting large amounts of radiation, including X-rays and gamma rays. The energy emitted by AGNs is thought to be powered by the supermassive black hole at the center of the galaxy. As the black hole accretes material from the surrounding environment, it releases enormous amounts of energy, which can heat up the gas and cause it to emit radiation. This process is often responsible for the extreme brightness of AGNs, which can outshine the rest of the galaxy. In some cases, the energy released by the black hole can even influence the surrounding galaxy, regulating star formation and impacting the evolution of the galaxy itself. 87. The event horizon is not a physical object, but a point of no return. The event horizon of a black hole is often mistakenly thought of as a physical surface, but it is not an actual object. Instead, the event horizon marks the point beyond which nothing can escape the black hole's gravitational pull, including light. Once an object crosses the event horizon, it is trapped and pulled toward the singularity at the center of the black hole. The event horizon is a boundary in space-time, defined by the escape velocity exceeding the speed of light. Although it is not a physical surface or edge, the event horizon has a significant role in determining what can or cannot escape the black hole's gravity. 88. Black holes do not necessarily suck everything in their surroundings, only objects that come too close. A common misconception is that black holes are like cosmic vacuums, sucking in everything around them. In reality, black holes only affect objects that come too close to them. The gravitational influence of a black hole extends outward, but objects that are far enough away from the event horizon will continue orbiting the black hole without falling in. For example, the Earth orbits the Sun because the Sun's gravity pulls on it, but it does not fall into the Sun. Similarly, a black hole can have planets and stars orbiting around it without them being drawn in, as long as they remain outside the event horizon. Only when objects pass too close to the black hole, crossing the event horizon, do they become trapped. 89. The mass of a black hole can be determined by observing the motion of nearby stars and gas. The mass of a black hole can be inferred by observing the gravitational effects it has on nearby stars, gas clouds, or even light. When a black hole is in a binary system with a companion star, the star's orbit is influenced by the black hole's gravity. By measuring the star's orbit, astronomers can calculate the mass of the unseen object. Similarly, by studying the motion of gas in the accretion disk surrounding the black hole, scientists can estimate the black hole's mass. The mass can also be determined by observing the velocity of objects that are being pulled into the black hole, or by studying the gravitational waves emitted during black hole mergers. 90. Supermassive black holes at the centers of galaxies are thought to play a major role in the evolution of galaxies. Supermassive black holes, SMBHs, which can have masses millions or billions of times that of the Sun, are found at the centers of most large galaxies, including the Milky Way. These black holes are thought to have a profound effect on the evolution of galaxies. As they accrete matter, they release enormous amounts of energy, which can regulate the formation of stars in the surrounding galaxy. For example, the energy released from an active supermassive black hole, an active galactic nucleus, or AGN, can heat the gas in the galaxy, preventing it from cooling and collapsing to form new stars. This process can prevent excessive star formation and shape the overall structure of the galaxy. In some cases, SMBH may even drive galaxy-wide outflows of gas, further influencing the galaxy's evolution. 91. Black holes might be able to power active galactic nuclei by accreting material at a high rate. Active galactic nuclei, AGN, are exceptionally bright regions at the centers of certain galaxies, often outshining the entire galaxy. These powerful emissions are thought to be powered by a supermassive black hole located at the center. As the black hole rapidly accretes material from its surroundings, the gas forms a superheated accretion disk. This disk emits vast amounts of energy, including X-rays, ultraviolet, and visible light. The energy produced is so immense that it can cause the AGN to outshine the rest of the galaxy, sometimes by a factor of several thousand times. The black hole's accretion process not only powers the AGN, but also plays a crucial role in the regulation of star formation and the overall evolution of the galaxy. 92. The information paradox questions what happens to information that falls into a black hole. The information paradox is a long-standing puzzle in theoretical physics. According to quantum mechanics, information about the state of a system, such as the position and velocity of particles, cannot be lost. However, when matter falls into a black hole, it seems that the information about the matter is lost beyond the event horizon. This creates a conflict between the principles of quantum mechanics, which insist on the preservation of information, and general relativity, which describes the black hole as a region where information is lost. Some theories suggest that the information may be encoded in the Hawking radiation emitted by the black hole, or that it could be preserved in some form at the event horizon itself, but no definitive solution has been found. 93. The study of black holes helps scientists understand the fundamental laws of physics. Black holes are a critical tool for testing the limits of our understanding of physics. The extreme conditions near a black hole, where gravity is incredibly strong and space-time is intensely curved, provide a unique environment to test the predictions of general relativity and quantum mechanics. Scientists use black holes to explore the nature of gravity, the structure of space-time, and the behavior of matter under extreme conditions. The study of black holes also opens the door to investigating some of the deepest mysteries in physics, such as quantum gravity, the nature of singularities, and the relationship between general relativity and quantum mechanics. Ultimately, black holes serve as natural laboratories for probing the fundamental laws of the universe. 94. A black hole's spin can significantly affect the surrounding space-time, creating unique features like the ergosphere. The spin of a black hole is one of its most defining features. A rotating black hole, or Kerr black hole, creates a region around it called the ergosphere. The intense rotation of the black hole causes space-time itself to twist and drag in the direction of the black hole's spin. In the ergosphere, objects and matter are forced to move in the direction of the spin, and even light is affected by this frame dragging effect. The rotation can also lead to the formation of relativistic jets, narrow beams of energetic particles shooting out from the poles of the black hole. The ergosphere is a fascinating consequence of a black hole's spin and plays a crucial role in how black holes interact with their environment. 95. Some black holes are found in the centers of globular clusters, which are dense groups of stars. In addition to being located at the centers of galaxies, black holes can also be found in globular clusters, dense, spherical collections of stars that orbit around galaxies. The strong gravitational interactions in these clusters can lead to the formation of black holes, which can be either stellar mass black holes formed by the collapse of individual massive stars or intermediate mass black holes. These black holes are more difficult to detect due to the crowded environment of the cluster, but astronomers have observed indirect signs of black holes in some clusters, such as the unusual motion of nearby stars or the emission of X-rays from a black hole's accretion disk. 96. Black holes may provide insights into the nature of space-time and the potential for time travel. The extreme warping of space-time near black holes presents fascinating possibilities for understanding the fabric of the universe. According to Einstein's theory of general relativity, the intense gravity near a black hole causes time to slow down, a phenomenon known as time dilation. For an observer far from the black hole, time would appear to pass more slowly for an object approaching the event horizon. This leads to the intriguing possibility that black holes could, in theory, serve as a form of time travel. Some theories suggest that rotating black holes might even create wormholes, hypothetical tunnels through space-time that could connect distant parts of the universe. However, these ideas are purely speculative and remain unproven. 97. The detection of gravitational waves has opened a new era in black hole research. The detection of gravitational waves in 2015, caused by the merger of two black holes, marked a major breakthrough in the study of black holes. Gravitational waves are ripples in space-time created by the acceleration of massive objects, such as when two black holes collide. The discovery confirmed one of the key predictions of Einstein's theory of general relativity and opened up a new way of observing black holes. Unlike traditional telescopes, which observe electromagnetic radiation like light and X-rays, gravitational wave detectors like LIGO can hear the distortions in space-time caused by black hole mergers. This new method of observation has already led to several discoveries, including the detection of multiple black hole mergers, and is expected to yield more insights into the behavior of black holes and the nature of gravity. 98. Black holes are not inherently dangerous to objects in space unless they come too close. While black holes have incredibly strong gravitational fields, they are not inherently dangerous to objects in space unless those objects come too close. The gravitational pull of a black hole only affects objects that pass within a certain distance, known as the event horizon. Outside of this region, the gravitational effects of a black hole are similar to those of any other massive object. For example, the Sun's gravity does not suck Earth into it because Earth is far enough away. Similarly, objects in orbit around a black hole can remain in stable orbits, and black holes only become dangerous when objects fall past the event horizon and are pulled toward the singularity. 1999. The study of black holes is closely tied to the study of the early universe and the Big Bang. Black holes are not only key to understanding the present universe, but also the early stages of cosmic history. Some scientists theorize that black holes could have formed shortly after the Big Bang, through a process involving quantum fluctuations in the dense, hot environment of the early universe. These so-called primordial black holes could have played a role in the formation of galaxies and structures in the universe. Additionally, the extreme conditions near black holes offer a way to study the effects of gravity and quantum mechanics on the fabric of space-time, providing valuable insights into the universe's beginnings. The study of black holes, along with cosmic microwave background radiation and other early universe phenomena, helps scientists trace the evolution of the cosmos. 100. Despite their mysterious nature, black holes continue to captivate both scientists and the public alike. Black holes are among the most enigmatic and captivating objects in the universe. Despite being invisible and difficult to study directly, they have sparked the imaginations of scientists, philosophers, and the public for centuries. From the first theoretical proposals by John Michel and Albert Einstein to modern discoveries, black holes have become a central topic in astrophysics and cosmology. The mystery of what happens inside a black hole, the nature of singularities, and the potential for time travel or wormholes continue to drive scientific inquiry and public fascination. As research advances, black holes will undoubtedly remain one of the most exciting and mysterious aspects of the universe to explore.